Thank you very much. We'll proceed with the next talk this morning. And this is Professor Richard McMahon from University of Cambridge, who's going to talk to us about the earliest stars and galaxies. Richard, thank you very much.
Okay, thank you. So it's my sort of pleasure to be here today, and it's sort of quite, I really enjoyed the first presentation, and I will actually mention the accelerating universe on one of my slides, and I sort of view it as not my problem. So I'm basically an observational astronomer. I work in the sort of optical, ground-based mainly, do some space-based, and I've worked on the development of the sort of technology, or use of technology, through my career. But I've also, this talk is quite broad, so I've actually drawn on some work of colleagues who happen to be in Cambridge, because I could get their slides, particularly Anke Aronson, who works on the Milky Way. It's a very important object, the galaxy we live in, and I'll come on to that. And then Sandro Takela, who has been involved in some of the James Webb results that I'll talk about. And so then this is just a history of the universe in one slide, similar to what we had earlier. I could probably talk to you for an hour on various elements of this. So the parts that I'm really going to focus in are, so basically, I work in terms of redshift, and I'll explain that a bit later, but effectively redshift is a method that we use to infer distance. Distance means then, because of the finite travel time of light, when we look at an object that's very far away, we are looking at the universe in the past. Okay? So that's the basic premise, and the universe was smaller in the past, and so therefore the wavelengths have been stretched effectively as the universe expands, and that gives us this redshift. And I'll sort of mention that again later. But so I'm not going to justify those assumptions. It's a model that was being questioned when I started my PhD in the 1980s, but that's now well established in terms of redshift being the estimator of distance and then of time. And so I have redshift is more or less log here, but basically, so this is the present day, and I've got 13.8 billion years for the age of the universe. The previous speaker had 13.7. These are this is two significant figures. Again, when I started my research many, many years ago, we were talking about factors of 2. Okay, so we're not going to get het up with this. This is, at least I'm not anyway. There are colleagues who get very obsessed, actually, about the second decimal place here, and I have a great respect for them. They're usually more... and hopefully they respect my views as well. Okay, so fundamentally, in the present day, we're talking about also what we can see, and so that's the sort of I'm going to come on to that as well. The 5% of the universe that's in what's called matter, and only actually most of that's highly ionized gas. It's mostly hydrogen and helium, and it's so ionized that we can't actually directly see it. It does imprint actually on the microwave background, which is another topic. And so I'm going to mention a little bit about work on the Milky Way, and then I'm mainly going to focus on what's happening up here at sort of around the billion year after the Big Bang. And then, okay. So just to put this into context, every atom in our bodies, apart from the hydrogen, has been inside stars. We are stardust. So we start out with the universe, it's basically 75% hydrogen, 25% helium, and somehow we get to a situation where we've now, in our bodies anyway, and the next speakers will come along to this, but basically the oxygen is made in stars. And it's multiple generations of stars, that's important. So it's stars that have formed, aged quite quickly, and then had supernova. They explode as supernova, they throw the material out, and then stars form again. And so there's multiple generations. That's a theory, I might add. We're sort of testing it as we go along. But it's a pretty self-consistent theory, I think. Okay? So what did the earliest stars and galaxies look like? Well, we don't know, actually, and that's why we're interested in the subject, right? If we knew the answer. As scientists, that's not our purpose. Our purpose is really to discover and question and discover new things. And it's really a field that is benefits from technological developments, maybe a bit of philosophical, mathematical theory, but I would argue that the breakthroughs come from technological developments. In the same way that Galileo used the telescope, and literally he made 5 major breakthrough observations in the first 6 months of having access to that piece of technology. Go through that, but it was 5, I think. Okay? And a lot of science is like that. We have questions, and that's where the physics comes in. They're physically based, and then we try to answer them, and we use technology for that. And we live in it's fantastic with the improvements in detector technology and cryogenics, and that is really what has driving, I would say, observation and astronomy. And so quite often, it's still exciting, right? Not every area of science, I would say. You can't guarantee that your area is going to be exciting in 10 or 20 years. It might be for you, but then it has to be exciting for other people as well, because actually that's why they pay you to do this work. Okay? Because I am paid by the taxpayer to basically answer the questions that I hope interest you. And so one of the questions that I was involved with 30 years ago, not anymore, is we set out to actually measure how much matter there was in the universe, because we didn't really, at that time, people believed that the universe was 99% dark matter. This dark matter that we couldn't see, but it was there by gravity. And so we set out to basically study high redshift supernova. And I worked on high redshift surveys, and I was asked, as a sort of technical guru, how to actually do that. And in some sense, I just give me detectors, we need some computers, we need telescope time, and we'll adapt some of the techniques that I developed for quasars, and we use that. And we got this results. We did not understand. We were expecting the universe to be slowing down, but it was accelerating. So for 2 or 3 years, we thought our data was wrong. And then, I think one of the theoreticians said, well, Richard, and my other colleagues, well, maybe there's something that you don't understand. And so we just published our results. So what's very important, we published, the result is that the universe expansion is accelerating. Dark energy is an explanation of that. Okay, so it's very important to distinguish what you observe, and then you try and explain. Okay, so I'm not saying that dark energy doesn't exist, but it's the accelerating universe that's the observation. And that's quite important, I think, to remember. And we're still not, currently what we're trying to do, or not me, my colleagues are plowing away, trying to get more precise measures of the deceleration, and also to see if the deceleration is changing with time. But that's way beyond, I think, my lifetime, to be honest. I think that's the other thing. Technological developments are the key. So then I've probably skip over this, because I've sort of covered it, but just to remind you, light travel time, it's 8 light minutes to the sun. And so most of the time I'm talking, and so M31 is 1 million light years away. We're talking, the objects I'm going to talk about, they're billions of years back in the past, and they're very faint. So that's redshift. Okay, so just to give some of the numbers, this is one of my undergraduate lectures. So this is just simply redshift versus look-back time, and then a bit of a table. So I've got different redshifts here. This is the look-back time. Here I've got, actually this is recombination, which is what the previous speaker was talking about. But basically I'm going to talk mainly about up here, about 400 million years after the Big Bang, and I'm going to talk about now. Okay, so, and the solar system, just to give you a bit of context, and maybe I'll be corrected later in the meeting with people maybe talking about this, but basically we believe the solar system itself formed around 5 billion years ago, and so basically, and also the thing about the solar system is that effectively the chemical composition of the sun is to first order what we're made of. So all those all the elements that that are in the solar system had to be formed earlier, apart from the hydrogen. Okay, so that's basically, in terms of redshift, it's around redshift of 0.5. Okay, so I'm just going to take you through a bit about the Milky Way, because it's sort of contextually. So this here is a picture of a piece of the Milky Way. And in fact, Galileo was the first to realize that he looked at the Milky Way. It was thought to just be a cloud. If you look up in a dark night, away from the centre of Oxford or Cambridge, wherever, okay, you might see in the summer this sort of band of light, which just looks like a haze. And Galileo, when he looked at it with his telescope, saw, not as clear as this, but he saw it was actually individual stars. So that was sort of one of the other breakthroughs. In some sense, he discovered that the Milky Way, as it was called, was actually appeared to be stars. So this is a piece of the small piece of the Milky Way. There's basically 100 billion stars in the sun, and the total mass, in the Milky Way, and the mass is around 6 by 10 to the 10 solar masses in those stars. I'm not including the dark matter. And I'll come on to this number later on. And so we sit here. This is a schematic. If you could sit outside and up above the Milky Way, we sit out here in the solar system about 10 kiloparsecs from the central region. And the center, we believe there's a, well, no, we don't believe, there is a, I believe, there's a massive black hole at the center as well. So this is probably, I think, a very spectacular, this is a picture, if you like, from Earth, of the structure of the Milky Way from a satellite called Gaia. So it's not a picture in the conventional sense where they just took a picture. What they did was they actually they're measuring the positions of every star in the Milky Way. And I was going to go and find, this very bright one might be Sirius. So that might be naked eye, actually. But that's the sort of galactic bulge. These are the Magellanic Clouds in the south. So basically what it's doing here is, what the satellite does, it scans very small pieces of the sky and then makes a catalog, a table, of all the stars and their colors, and then this image has been constructed from that. And it's basically, that's a satellite, it's a European Space Agency satellite. The satellite also measures the distances to the stars very precisely, which is quite good. Okay, right, so I'm going to just talk a little bit about, first of all, galactic archaeology. So I'm going to talk about the Milky Way. So the basic idea is that you have some stars that formed, well, some of the stars in the Milky Way formed a very long time ago, and they haven't gone into supernova, okay? So we can, in some sense, find stars, and you might call them very old, but they were formed when the Milky Way was very young, and these stars have they are much lower metallicity. And so therefore, by studying these stars, we're learning about what the universe was like when those stars formed. Because as I mentioned earlier, the solar system and the sun formed 5 billion years ago, which is on this scale around here. But there are stars in the Milky Way which we believe formed a few hundred years after the Big Bang. Sorry, a few 100 million years after the Big Bang. Or redshift 10. I work in terms of redshift because the units don't matter, right? So thousands, billions, sorry, I don't remember those numbers. It's very important to work with, sometimes with units between 1 and 10. Okay, so some of the stars in the Milky Way formed a very long time ago, and now they're in the Milky Way. So if you look at the picture of the Milky Way, some of them, this yellow star, and this is a credit from Anka. So then what you do is, they're very rare, because most of the stars in the Milky Way did form more recently. I'll come on to that in a moment. And so basically, but there are people who spend a lot of their whole lives looking for these very metal-poor stars. Anka's quite young, so she'll be doing it probably for the next 40 years. Okay, so these are basically, in some sense, ancient metal-poor stars. They're effectively witnesses of what the universe was like, back. And they're also, to be honest, because they've got metals, some of them, they themselves are descendants of the first stars. Okay, so these are, so here I'm talking about, in some sense, the earliest stars that we can observe. Because I'm an observer, so when every time I'm speaking, I'm talking about what we can see, because I'm an experimentalist. Okay, so this is just another. But they're very rare, so they're basically 10 to the minus. And so just in terms of numbers, for every hydrogen atom in the star, there's 10 to the 9 atoms of hydrogen, for every iron atom. And this is just to show you the spectrum. So spectrum is what we use it's like a barcode, how to measure chemical compositions. So this is a piece of the spectrum of the sun. And so all of these, what look like noise, are actually chemical elements. So if you're familiar with what's called the Fraunhofer lines in the spectrum of the sun, that's effectively that's what they are. So this is not noise, this is actually individual chemical transitions. And these two here are actually, I think, calcium, what are called calcium H and K. And so this is an ultra metal poor star where you're only seeing absorption in them from hydrogen. So this is what's called the hydrogen beta line, hydrogen beta lower lines, and I think there's a bit of calcium here as well. So even these very metal poor stars have metals in them, okay, which is a sort of, and then it needs to be sort of understood. Okay, so that's the sort of bit of context in stars. So I was going to talk a bit more about the oldest stars in the Milky Way, but if you go to Wikipedia, you discover that the problem with measuring the age in stars, we don't have a clock, so you have to use theory to compute the age of a star from its properties. And what was the oldest star at one point was thought to be, well, the theoretical models were saying it was older than the universe. Okay, so that tells you that one of those two numbers is incorrect. Okay, right? And in this case, it was discovered that, well, no, rephrase it. Somebody did new theories, ran some numerical models, and were able to bring its age down by, I think, 2 billion years. Okay, so that was, and I wasn't up to date in that area, I might add. So that's why I started doing the slides, and then I had to realize, no, this is out of date. But certainly, when we talk about metallicity, that is something that we can measure. Okay, so that's sort of the dilemma sometimes. But you'd like to know the age. Okay, so I'm starting out with, this is M31, which is you can see, you could also call them what are called the Magellanic Clouds. They're galaxies as well. But this is the only galaxy we can see from the northern hemisphere, spotted by Messier many, many years ago, and just as a nebula. And I think it's also interesting that it's almost 100 years since we discovered what's called the Great Debate in the 1920s about whether these nebula were in the Milky Way or outside. So that was step one. There was realization that they were outside, and then Hubble discovered that the ones that were fainter, effectively, were moving away from us faster. And that came in about 1923. So the expansion of the universe happened, that discovery happened within 3 years. And that was a technological thing almost, I would say, because he was able to measure these velocities and then he plots a graph, very simple graph. And so, okay, so the key thing here is this is I'm not too sure where the image comes from, but this is how far away it is in light years. Okay, so this is just on one slide again. It's trying to sort of take you through the sort of, I guess, so as I said, I've mentioned this, where the atoms in our bodies have come through stars that have formed and then gone supernova, and then new stars have formed. So this is a compilation of, so it's redshift and along the bottom, which is what we measure, and then this look-back time is what we compute using a cosmological model, and so this is effectively, it's a very similar plot in terms of, but it seems to be consistent. So this is now, okay, yeah, so the difference is that it's flipped. So this is here and now, so the star formation, the average star formation rate, the Milky Way is still forming stars, So if you look at the Orion Nebula, it's still forming stars. So it's not that the Milky Way is still forming stars. And so there's many galaxies in the nearby universe which are forming stars. And this is the sort of rate of star formation per year in a sort of what we call cubic megaparsecs. And so one of the results that came in the sort of earlier part of the 21st century was that between redshift, well, it was in the 1990s as well, up to redshift of 1, that the star formation rate is rapidly increasing. Well, it's increasing in the past or decreasing towards now. So that's another thing that when we speak, astronomers will increase and decrease. You have to translate that because it's going to depend on the sentence. And so basically at around redshift 2, which is the look back, so the sun, as I said, is forming around here. We now find that there was a peak. The star formation rate peaked on average at around redshift 2, and then it drops. Now, the problem is, at some level, that above redshift 2, the star formation rate is dropping. That makes it harder to observe the objects, because whenever stars are forming, they tend to be brighter, at least the ones that are short-lived. And so this region up here has very little data, partially because the objects are far away and faint, and also there's technical issues as well. And so I'm going to come on to those. So this is, we've got lots of data nearby, and then this is what our current best picture of the star formation rate with time. And so, so we believe this is where the first galaxies are forming. And then previously it was dark. Okay. So this is just a historical sort of retrospective, and this is a plot that I made before, well, probably the dates on the plot actually. So this was before James Webb. So this is showing you how the field has progressed since the 1960s in terms of finding high redshift objects. Because the motivation was to find objects that were young, you would look for high redshift objects. And there was different populations. So there was a major breakthrough effectively in the 1960s with the discovery of a new class of object called quasars. These were supermassive black holes. So you quite often in scientific research, you make a breakthrough, there's a leap. So we were up to redshift 2. What I call conventional normal galaxies like the Milky Way, that's the red line. That has taken until the 1990s to get to the same redshifts. And it's now actually, as I'll show you, so the blue line is black holes, and then the red line is the galaxy one. And so prior to JWST, but so it's slowly growing, and a lot of these, every now and again there's a bit of a kick because it's usually a technology. And so this kick up here, for instance, is Hubble, basically. The period here didn't change a lot in the noughties, effectively. But then basically Hubble, observations have resulted in all of these changes. And that's a technological thing. Okay, so this is the sort of current version of that in terms of the earliest galaxies. And so Hubble was launched in 2021. And so we've gone really from sort of redshifts. I think that this actually might be a Hubble object, to be honest. And so we were at redshift 9 before before JWST, and now we're up to redshift of 14. So I'm going to show you some of the observations, those exciting observations, which have come in the last year. Okay, so this is just to highlight the problems. This is a very deep picture of a small patch of sky. These are the stars. They have what are called diffraction spikes, because they're point sources. You get diffraction on the structures which are holding the telescope optics in place. And galaxies are more diffuse, so you don't get diffraction spikes. So when you look at a picture like this, the question is, you cannot measure the distance to every object. Okay, so this is just a picture. So if we want to measure the distance, you can't go out with a tape measure anyway, right? So we have to point a telescope, and we do it one by one. So what we do is we develop techniques to select which objects we think are at highest redshift. And fundamentally, it's the redder objects that are at higher redshift. And the reason that high redshift objects are red effectively is because the hydrogen that makes up 75% of the material in the universe absorbs the radiation in the rest frame UV. So you then shift, so what you get is a step effectively in the spectrum of the object, and therefore the objects, when you redshift them, they've got no blue light. Okay? Whereas other objects which are flat, when you redshift them, they still have blue light. And so this is an image that's created with James Webb, and all the radiation actually is in the near infrared. This is micron wavelengths. And so just looking at this image, these will be the highest redshift objects, but where highest actually means probably a redshift above 4. There's degeneracy on this. And people have been caught out by it and basically made mistaken claims. So for instance, there was a lot of excitement early on from James Webb that a group was claiming they'd found an object at redshift 20, and when they actually measured the redshift, it was 5. Okay, so it's not, and that's another sort of talk. So this is just, again, just to emphasize the difference between Hubble and James Webb. This is just to give you an idea of the size. James Webb is a larger telescope. It's also segmented, and that was very, very challenging, and many of us really were concerned that that technology had not been tested before, but NASA claimed that it had. Yeah, okay, so it works, it's bigger, and it's also infrared wavelengths. So I'm going to just jump. It's very far away from the Earth, so let me just jump to the current status of last, say, June 23. So basically, in June 2023, this is sort of, basically there were claims for very high redshift objects, but up to redshift 10, but actually none of them were confirmed. So I'm going to just jump. So this is now how we measure a redshift. So we take a spectrum, and so this is all in the near infrared, which is not visible to the eye. And the signature that tells us that this object is at a redshift of 14 is this sharp break. Okay? So this sharp break is caused by hydrogen that's just in the universe, because the universe is 75% hydrogen. Most of it's highly ionized, so it's just protons and electrons flying around. But there's a small amount of them in the neutral state, and this causes this absorption edge. And it's completely black. Okay? So, and there's just enough hydrogen. And that doesn't come from theory. Okay? This is an observation of the universe. The universe, fortunately, it's been kind, at some level, I would say, to have things that we can observe. It didn't have to be like that. So people who work on the CMB and who want to look at the earlier times, the universe is opaque. They really, really, really have to think much harder than I do about how to interpret their data. Okay, so okay? But this is categoric. Now, what happens is that people, if you have a lot of noise down here, and I could show you some, it doesn't go to 0. And that's how people have made the mistake in the past, where they claim an object is at this sort of redshift, but actually it's a lower redshift object, and the way you rule it out is by going in here and getting a very high signal-to-noise spectrum. But this is all, basically, this is part of the spectrum. This is the observer at micron wavelengths, which Hubble doesn't work at. Okay? So Hubble effectively is big. Sorry, JWST is larger, but the more important thing is that it actually works at near-infrared wavelengths. And also, it's above our atmosphere, because the atmosphere, you look outside in the winter, it looks dark, but not at these wavelengths. The atmosphere is glowing. And so that's why we put things into space quite often, because the atmosphere is just so bright. Like, I think it's basically at these wavelengths, the atmosphere itself is glowing. The ozone layer is about 1 million times brighter than going into space. And so that's, okay. So then just how old is this object? So I've done it for 2 different cosmologies. So one is the sort of, I think the Planck one, actually, well, yeah, the 13.7 universe. And then there's one that I use, which is the one significant figure universe, which is called the consensus universe, which is H naught is 70, omega is 0.3, and omega vac is, or dark energy is 0.7. And I've been using these numbers for 20 years. And so, because in some sense, it's good enough in my area, because, okay, the age of the universe is different by a couple of 100 million years, but actually, at high redshift, it's not a big difference, okay? So it's not that I'm being lazy, it's just that it's good enough, okay? And you can actually go, there's quite a cool calculator, you can go and you can put in whatever your favorite cosmology is, but that's how old this object is. It's 300 million years after the Big Bang. In terms of its properties, its mass in stars is around, this is in log, so it's 10 to the 8. So it's 100 times less massive than the sun, so Milky Way. And so, and that's what we expect, because we believe galaxies grow, actually, nowadays, by merging over time, okay? And they're not forming in one great big. We did actually hope, many, many years ago, I was involved in a project where we tried to find galaxies that were forming that were more massive back in time, because that was the sort of, at that time, that was the theory, but we didn't find anything. So that was a failure, and so we've sort of had to wait for Hubble. And so the star formation rate, there's different assumptions, but so the key thing here is also the measured star formation rate, which is around, say, here, say 4. It's got large error bars. There's enough time for the galaxies to form, okay? Because that's another problem is that we would often have, finding galaxies, you measure the star formation rate, which is their growth rate, and their current mass, and there wasn't sometimes time for a very simple model for the galaxies to form. So I think this is, I would say, not unusual up to a point. Okay? So this is the sort of where we are in the subject. So this is a busy plot, but it's got age along the bottom here. So as a result of JWST, we now have about 100 galaxies that might be above redshifts of 8. The only ones that are spectroscopically confirmed are the red ones. Okay? So, and the red ones are also the brightest ones. And there's people actually here at the University of Oxford have been working on some of these objects. Now, theoreticians from first principles do have difficulties, some, with forming, I think, this object, because it's quite bright back in that time. But I think, again, they just need to tune their parameters. Okay, this is just back to this. And then just where I think the subject is going, and it's a bit biased. So in terms of the Milky Way, there's a new instrument that we are building which will allow us to take 3,000 spectra of stars in one go using fiber optics. So we can basically locate and just put a fiber onto different 3,000 at the same time. And so that will allow us to take 3,000 spectra all in one go. And so I expect that it's going to do a range of different scientific projects. This was a UK telescope that was purchased whenever, I get emotional about this. When Labour came into power after the Thatcher years, there was an opportunity to bid for funding, and I was the one who basically proposed that we would build a telescope in Chile that was better than anybody else's to do surveys, and we're still using it, okay, which is quite exciting. But basically, this will allow us to find more stars. It's not going to be so important for high redshift galaxies because you really have to go to space for the highest redshift galaxies because the sky is very bright. So it's optical, and it's also high dispersion, so we can actually do all the chemicals. So it's high precision. In terms of earliest galaxies, the ones that we can see, I think Webb in principle can get us out to redshift of 20. It'll be hard and challenging because of the problem is that you need high quality data because there's so many, 99.999% of galaxies are in the foreground. And so you need very high quality data so that you don't get interlopers that are misclassified. Another exciting possibility is to use, when a star explodes, that they can actually, some of them can be lensed. And so, again, in the near infrared, in principle, we might be able to find them up to redshift 20. And then, so that's using stars. And then another project that I'm involved with at the moment is we're building something called the Square Kilometre Array. So this is a radio telescope, which is part of it's going in South Africa and parts going in Australia. And this will look for hydrogen. So it's going to try and detect hydrogen using the fine structure 21 centimeter line. And so we can't detect stars, but the basic idea is we should be able to see the regions around the first stars, because the first stars are believed to be very hot, and they produce ultraviolet radiation, which will basically ionize bubbles in the gas. And so we hope that we'll be able to see, not directly the stars, but we'll see these bubbles in neutral hydrogen up to redshift 20. Basically, that is so, and that, I think, is probably, you'll get maybe younger people coming along and talking about that one in 10, 15 years. I think it's that far off. But I think the subject is, that's the direction, in my opinion, it's going. Okay.
Thank you very much, Richard. Okay, to take some questions.
Yeah.
Any questions?
Yeah, great talk. Thank you very much. I was just wondering if you could talk a little bit more about the peak in star formation rate, and is that due to the supply of interstellar material running out, expansion winning out over density, or maybe there's not any more clumping around strings of dark matter?
And let's not invoke dark matter. We don't need the dark matter for that, I think. But basically, I think the idea is that material is collapsing. Okay, so, and then we are sort of running out of material, effectively, to basically falling into galaxies, effectively. That's, I think, the current picture. Okay. The original idea was that you'd have galaxies, this would all happen at earlier times. And actually, this would be lower, actually, to be honest. Okay. So basically the idea is, our current picture is that you get small clumps forming first, and then material is accreting in, and then you form the stars, and you're running out effectively of, the ionization does matter. Yeah, okay, so I think, so there is, it's an interesting question whether, yeah, I think that's, you're sure now but it's a bit complicated, but I think, yeah, but it's, I think, but that's, yeah, I'm not there to see. I sort of very much, this is what we see, and I've been focusing really on up here, but this was, yeah, okay, so, but the material collapses, and you run out of material. There's also something called feedback, which I didn't, okay, so that, for instance, okay, we talk about how important dark matter is. There's another class of theories that for forming of galaxies, that galaxies should have already collapsed much earlier. But what happens is the stars, when they go supernova, produce radiation field and eject material. That sort of slows the collapse down a bit, so this collapse. And then the other one is there's basically supermassive black holes in the center of galaxies also produce a lot of. So they have 1% of the mass, but nuclear synthesis, right? If you burn all the way from hydrogen up to iron, 1% of the rest mass goes into energy. Okay? If you drop a kilogram of material into a black hole, you basically get half, well, E equal to mc squared. Right? In principle, you can get, and so we have these, we have supermassive black holes in the Milky Way. And so I often tell my children and my friends, well, those people have said this, if we hadn't had supermassive black holes to slow down, because there seems to be more supermassive black holes in the past, accreting, okay? So you have a supermassive black hole in the middle of the Milky Way, but it's not accreting at the moment, so it's dark. So it's a massive dark object. But the quasars that I will still work on, they are accreting a lot at earlier times. So they're producing a lot of radiation. And so we believe it's a and it's not clear which is the supernova produce feedback, and so that has also slowed down this here. Okay? So it's complicated. It's not just running out of material. There's just these feedback mechanisms which we don't understand. Again, that's not my problem.
Just thank you. Just
it's my get out of fee jail card.
Just behind, if you could pass the microphone to the row just behind. Thank you. There's just one there. Thank you very much.
Yeah, thank you for that. It's actually concerning the same slide, so good. Thank you, Andy, for the previous question. I just didn't understand before. I think you explained, but is the drop-off towards the beginning of the universe on that slide because we don't see the star formation, or because it didn't happen?
Because it didn't happen, basically.
It didn't happen, okay. Because
it's just
you need time for the gas clouds to...
Okay. You need time for the gas to... The universe starts out smooth.
Yeah.
Okay, right? Totally smooth. And we see these small ripples in the cosmic microwave background, which are 10 to the minus... Yeah? Okay. And so those ripples, effectively, are the starts of the universe. Because the universe is it's random, right? So you have to think of the universe... We get taught it's smooth, but actually it's noisy. And so in this smoothness, you just get clumps of the universe where it's just a bit above average. And they accrete very slowly more material. And the galaxies form in what we call the 5 sigma peaks. So this smooth universe has noise peaks, okay? And so different parts of the universe, what we call turn around earlier. So you've got the universe expanding, but then there's pieces of the universe. You've got the expansion, but there's enough material that it collapses. So that's the contest is the universe is expanding, and you have to wait for the material to curdle effectively at some level. Okay, so that's what is happening here. Okay, so basically very early. So it's, and in some sense, again, the fluctuations in the microwave background. I'd have to go back to my textbooks from 30 years ago. Were they stronger or weaker than we were expecting? I mean, that's the sort of because people had predicted what the fluctuations should be, and it's linked to dark matter. Actually, that's. Okay, so these fluctuations have, the smooth, these clumps have to grow because they're matter. Sometimes that is matter, and will collapse. Okay, yeah. Hope that answers it.
Speculation, and if you said it's slowing down because of all the outward pressure, but there's still enough hydrogen around, would you expect then, as time goes on, a second peak of another star formation maximum later on? In another few billion years?
Well, I think, no, we are. Okay, I think we're right. Okay, so the other thing that happens is the universe has grown. So the protons, when we talk about hydrogen, what we're really talking about are protons and electrons. And they're now so far apart, again, that what's called the recombination time. So, you require the proton and the electron to get close together. And again, I used to have these numbers at my fingertips. So therefore, as the universe expands, and that's again back to, it is expected to be getting colder, and the atoms just don't become neutral. It just stays ion. Well, we would call it ion. You think of ionized gas being hot, but actually it's just the protons and electrons are just very far apart. Okay? So that was the picture that the universe would expand and become cold and dark. Now, when we set out to measure the mass of the universe, the idea was that maybe it would slow down and then turn around. So you would collapse again. But I think that is now, well, because of the acceleration that we observed, we don't expect that to happen. But that was being postulated at the end of the last century, that there would be a bounce, effectively, and maybe cyclical, basically, if that makes sense. But it wouldn't affect life on Earth, because it would be many billions of years' time before the universe would sort of fall in on itself again. Okay? But at the moment, it's expanding. The protons and electrons are just so far apart. We say it's hydrogen, but really it's protons and electrons. So it's sort of...
Okay. Thanks. Any other questions? Wave dramatically. Yes, just at the back there, please. Thank you.
Hi, thank you for that. I was thinking back to some of your slides at the beginning about the ultra-low metallicity stars in the Milky Way, and then trying to relate that to that star formation slide that the previous questions were looking at. So the stars that are low metallicity close to us are really ancient, and they're slowly evolving, which means that they're very small. Presumably that then means that if one looks at the mass distribution of some of the truly antediluvian galaxies, they would have consisted of lots and lots of very, very large stars. And I guess, does that then explain, our evolution? Because the large stars have just evolved through, exploded, and then formed new stars, and so on and so forth.
Okay, so I'll try and answer part of the question. Yes. So these stars are, by definition, have masses less than the mass of the sun. Okay, because I said that the sun has what's called a main sequence lifetime of around, and the main sequence lifetime is the lifetime. You've got the hydrogen and helium burning as fusion. When you sort of run out of the hydrogen and helium, the star fundamentally isn't producing enough energy to keep it up. Basically, because the sun effectively is in thermodynamic equilibrium. You've got the central radiation coming from the center, stops it from collapsing. If there was no fusion happening at the center of the sun, when it stops, it'll collapse. And so that's another sort of story. These stars, because they're older than the sun, they effectively have lower masses. I think they're half a solar mass. Now, they don't produce much ultraviolet radiation. So there's a bit of a bias. When we look at high redshift galaxies, we're looking at them in the rest frame ultraviolet. So we're actually only detecting the most massive stars. And those are probably around, say, 20 to 100 solar masses. The other correction factor that people sometimes don't mention is that most of the mass in a galaxy is in the low mass objects. It's not in the massive ones. So we have to have what's called the initial mass function. So it gets quite, there's a lot of assumptions going into things here. But fundamentally, the first thing is, yes, these stars are lower mass than the objects that we see that we observe at high redshift. Okay, we directly are observing more massive stars, and basically, but yeah.
Okay, we're going to have to leave it there. But thank you so much, Richard, for your talk.